Okay, so hi everybody. My name is Toni Breshears. Today we're going to be doing Stats and Probability, Module 1, Chapter 13. Let's get started. Okay, so question 1. The students who took the final exam in problem solving in mathematics have the following scores. Complete parts A, B, and C below. Okay, so A. Explain how you can identify the typical score is by scanning the data. Okay, so our data is here in this table. So these are the scores that everybody got on their final exam. So the typical score made on the final exam is the score that people receive the most. To find the score, you can create a dot plot. So now we're going to go to our dot plot. So that is part B. Make a dot plot to organize this set of data, which is our table here. So really what you do is you go and you find your lowest grade made on the final, which is 43, and then you go and you find your highest number made on the final exam, which was 96. And then you go and you create your dot plot and you put however many dots um, for however many students made that grade. So if you look here, our first one was a 43. So I went through and I checked all of our finals, and then there was only one student that made a 43, so we get one dot there. If you go through, 44 had one dot. And then it kind of goes up from there. Like, we didn't have anybody make a 45 through 54. So we went straight to 55. One person made a 55, and then you go up to 62. Only one person made a 62, and then so on and so forth. Now, when you get to 75, we actually had two students who made a 75. And then when you go up to 77, two people made a 77, two people made an 80, two people made an 81. But to find out what the most who made, like, what grade was made the most, we'll go over and we'll see that 87 actually had three students. It was the only um, exam score to be made by three students, so that would be the most frequently made grade. So now part C. Using our data, we are going to make a stem and leaf display of this data. So we have our dot plot here because I thought it would be the easiest to use to make a stem and leaf display. So this is our stem and leaf display. So this is our stem, and then here are our leaves. That's pretty much how I say it. It's kind of like a flower growing up, and our different stems that are branching off, and then there's the leaves that are attached to each stem. So now if we start here, it goes through our 40s. The grades go through 40s, 50s, 60s, 70s, 80s, and 90s. So that's pretty much what these represent here. Now the numbers over here is actually the number in our ones place. This is the number in our tens place on our numbers, and this is the number in our ones place. So we start with our 43. So here's our 4 and our 3, our 43. Then we have 44, and then we have 44. So it goes on through there, and then we have 50, 55. And then just to scatter around, we have 75, which 75 was done twice. So we have 75 and then 75 again, because we had two students make 75s. So now it goes all the way up to our 96. So, and then our 87, which was the most frequent, we have 87 done 3 times. So next, question 2. At the same time that heights of the boys at a high school were studied, heights of the girls were also studied. So we're going to use this data here to complete each parts of our questions that are coming up. So it says, part A, create a table with the first column listing the frequency of each height, and with the second column listing the height relative to the frequency. Okay. So this is our heights and this is our frequency. So our height is however tall the girls at the high school were. So let's see our heights here. So we have our height was 57, 61, 63, 64, 65 here. And so what we did was 57, we go through, and if you go through and you look, 57 was a frequency of 1. Frequency is how many times something occurs, how many there is of that thing. So we only have 157. Luckily, they actually put the data in order for us, so we don't have to go searching. So 57, there was 1, which we have our 1 here. 58, there was 1, 2, and 3. So we have 3 here. 60 was 1. 61 was 1. 62, we actually had 1, 2, 3, and 4. So our frequency is 4. And it goes all the way down to our 73, which there was 1. The most common height for these girls, though, is 65, because 65, there was a frequency of 5. So now on to part B. Okay, so use Excel to create a histogram to summarize the data set above, which gives the heights to the nearest inch of 30 girls at the high school. Use intervals 1 unit wide, centered at the whole number values 56 and 57. Okay, so pretty much what we're doing is we're making a histogram. A histogram is like a graph. It seems to be a bar graph, if anything. So here we label, it's our high school heights, which is what I labeled it as. And then these are the heights of our girls. And then this is the frequency of their heights. So like I said previously, we had 5 girls that were 65 inches tall. So there's our 5, 65 and our 5. So this is pretty much what a histogram is. It summarizes the data. So it's not in, let me go back. So it's not in this form or this form. It's showing you more of a visually about how greater something is, but visualizing it. Okay, so write a description of the distribution of the heights of the girls. Okay, so the distribution of the heights is pretty much, what's common, what do you see out of these heights, what's your description? So pretty much the most frequent height of the 30 girls is 65 inches. That's pretty much, your point of view on what you see from the histogram here. So that's pretty much when it says write a description of the distribution of the heights of the girls. It's asking you to describe something you see from the graph here. Okay, question 3. Miss Smithson earned $66,000 per year, which she spent as shown in the table below. Draw a pie chart to show how Miss Smithson spent her yearly income. Use the data set to complete each part below. Okay, so part A, we're going to create a table with the first column listing the expenditure category and the second column listing the expenditure percentage relative to Miss Smithson's income. Okay, so this is what we have. Her taxes were $20,000, rent was $12,800, clothes were $2,000, insurance was $7,200, charity was $8,000, savings was $3,000, car payments was $6,800, food was $4,000, and miscellaneous was $2,200. So this is what our expenditure category is. It's our taxes, rent, clothes, insurance, charity, savings, car payments, food, and miscellaneous. And so, what it's wanting is us to switch the money into percentage. So let's say, how do we switch the percentage? So let's say charity is 8,000 of the total amount of 66,000 that she has. So if you take the 8,000 and divide it by 66,000, it gives you 0.12. And if you move the decimal place to the right 2 times, then you have the percentage, which is 12. So that means charity took up 12% of that amount of money. So now if you go over here, taxes was 30%, rent was 20%, clothes was 3%, insurance is 11%, charity was 12%, savings is 5%, Car payments 10%, food 6%, and miscellaneous is 3%. And what you can see by looking at the expenditure category and the expenditure cost, you can see that they are actually the least, it's the least amount of money she had to spend. That was the least amount of her cost, was her clothes and her miscellaneous, because they only were 3% of the amount of money she had. So now, moving on. So we're going to make a pie chart showing the expenditures percentage relative to Miss Smithson's income. So here it shows us everything that, everything's labeled here, and then this is our percentage. A pie chart is pretty much showing us in more of a visualized way, like a picture way, showing how big and how little amount of space or however much it took from something. So taxes, you can see it's 30%. That may not sound like much, like, if it was 50 or 100% of everything, but you can see that taxes did take the most of the $66,000 that she had. Rent took 20%, which is the second highest amount, and then clothes was 3%, which, like we know, was miscellaneous, was also 3%, which is here, but clothes was 3%, insurance is 11, charity was 12, savings was 5. It's not the smallest, but it's pretty, it's pretty low as well to the amount of money that she had put back in her savings from the 66,000. Car payment was 10%, food was 6%, and the miscellaneous, we're back to that, was 3%. So this is a representation, a picture, a pie chart of her expenditure percentages. So now, question 4. The pie chart shows government sources of revenue for the calendar year 2011. Use the chart to complete parts A and B below. Okay, so part A is, what is the angle measure of each of the 5 sectors representing income? Okay, so here's what we know. A full circle is 360 degrees. And then to find the angle of each sector, you must turn each percentage into a decimal and multiply by 360. All parts should add up to 360 when added together. So where income came from. So here we have blue, which is personal income taxes. Red is borrowing. Green is corporate income taxes. Yellow is miscellaneous. And purple is Social Security. So when you go and look down here, borrowing is 30%. Corporate income taxes is 4%. Miscellaneous taxes are 11%. Social Security is 22%, and personal income taxes is 30%, which by looking here, we know that our borrowing is our largest and our corporate income is our smallest. Which is the great thing about visualized pie charts and, graphs and stuff like that, because they show you visually and they make you understand clearly. Okay, so now we're going to find the angle measure of each of these. So what we did was our 33%, which is borrowing, we turned it into a decimal, which when you're turning something into a decimal, you move the decimal 2 places. And so it turns our 33%, our 33% into 0.33 times 360 equals 118.8. And when you round it up, it's 119 degrees. So that is the angle of borrowing. Now our corporate income taxes is 4%, but if you move our decimal 2 places, it makes it 0.04, which is 14.4 degrees. So 14 pretty much it's the 14-degree angle. So now our miscellaneous taxes is turns in from 11 to 0.11, and that becomes 39.6 degrees, which when we're going to continue to round, it makes it 40 degrees. And then now our Social Security, which is 22%, we make it into 0.22, which multiply that by 360, you get 79.2. You round it, you get 72 degrees for your angle. And then Lastly, personal income taxes, which is 30%, we turn that into 0.30, multiply it by 360 degrees, and we get 108 degrees. So now when you add your 119, your 14, your 40, your 79, and your 108, you get you get 360. Oh, okay. So I messed up here. This is actually supposed to, where it says 72, it's supposed to be 79. So anyways, but this calculation was right here. I just didn't write my 79 here. But anyways, it would equal up to 360 degrees. So that completes our full circle. That goes to show that our degrees, our angle measures were accurate. Okay, so question 5. An insurance company printed a brochure with the pictographs to the right, showing the growth in company assets over the period 1995 to 2007. Okay, so here's what we're going to do. We're going to explain how the pictographs do not accurately indicate that the assets, which were $4 billion in 1995 and $8 billion in 2007, or might want to assume from the pictographs that the assets were actually much greater in 2007 and 1995. Okay, so if you look at it, this pictograph is actually deceiving. It's because how the pictures, they don't match the exact height they're supposed to represent. The company assets are supposed to be at 4 billion in 1995, but the picture goes above 4 billion. If you look here, I actually placed a bar, and you can see that the house is actually over the bar. So that could say that it's, it's over 4 billion, and people might get the wrong idea. And if this was on a math test and you didn't have multiple choice, and it didn't give you like 4 billion and then something like outrageous like 6 billion after that for one of your multiple choice questions, you would choose you would say that this is about 4 billion because that's what it looks like, but really it's over the line, so it is not. And it's supposed to be, though, so that's what makes this deceiving. Now, if you look at 2007, 2007 is actually supposed to be 8 billion. So if 2007 is supposed to be 8 billion, you look closely here, it's not accurate either. It's actually way over the line here than it was down here at the 4 billion. So this is why this pictograph is very deceiving. It's not accurate at all. So that could be an issue. So now question 5 continued. What is the ratio of the volume of the large building to the volume of the small building? Suppose both buildings were rectangular boxes with the linear dimensions of the second, just twice those of the first. So pretty much this is what we could say here. The larger house is at 8 billion and the other is at 4 billion. The larger house is pretty much 4 times the volume of the first house. So that's pretty much how you would say that, because it is 4 times bigger. Like this, it goes 1, 1, 2, 3, and 4, and then you go 1, 2, 3, and 4. So it is 4 times bigger than the 2007 assets is 4 times bigger than the 1995. So, okay. Explain why it would have been more helpful or honest to print the actual asset value for each year on the front of each building. Okay. So it would have been more helpful to print the actual asset value for each year on the picture so that the entire graph would not be misleading. The amount that each year represents would be clearly represented. So if they were to put 4 billion above the little house, you would know exactly that that is what that little house represents, is the 4 billion, that it is supposed to be at the 4 billion mark. So you wouldn't have to sit there and draw the line above it or anything like that. You would know that that house is exactly 4 billion. so it would not be misleading at all. You would know the exact amount that it's supposed to be. Same thing with the assets of 2007. This picture goes over the 8 billion, but if you were to have 8 billion above this like the number 8 billion above this house, or here on the sidewalk, something like that around the house, just something to indicate that that house is supposed to be 8 billion, there would be no misleading. The picture would no longer be misleading because it would be established that the little one is 4 billion and the larger one is 8 billion. Okay, question 6. So using this data here, we're going to create a table that represents the data. So we have population in millions, and then we have what the population, what the year was for each of the populations. So what we have here is 1960, we had 2.11, which was 2.11 million. 1965 was 2.32, 1970 was 2.68, 1975 was 2.88, 1980 was 3.18, 1985 is 3.45, 1990 is 3.85, 1995 is 4.13, 2000 was 4.83, 2005 was 5.78, and then 2010 was 6.77. So that's pretty much, I mean, it's just a table. It's a simple, this is also a table, but it's best to show the different ways that you could create a table, but that is one way. Okay, so now we're going to create a line graph. So a line graph is going to show us pretty much throughout the years whether the fluctuation of our population in millions. So here we have population through the years. That is what I decided to name the line graph. So here on our axis, population in millions, which is our 0 to 2 to 4, 6 to 8, but that's in millions. So it's gonna be 2 million, 4 million, 6 million, 8 million, and then down here I have the years. I did it per every 20 years pretty much. So 1940 to 2020, because our graph goes from 1960 to 2010. So I just thought to give it a little bit of space. You don't have to start, like, I didn't have to start exactly at, the 1960, but whichever will show your graph the best. And so here's what I did. So at 1960, it was at 2.11. So you can see here, it's not on 2 million, it's a little bit above. So that represents our 2.11. And then 1965, it went up to 2.32, and you can see that it slowly, gradually goes up. We'll go here, 1980. At 1980, it was 3.18. So 1980, we don't have, here at our graph, it doesn't show exactly our 3, but we know that halfway would be right about here. And so if you see that at 1980, it would represent our 3.18 being right here. What's cool about a line graph is you can see where, at what year or near what year our population actually shot up the fastest, what years had the biggest growth. And so here you can see it shot up around from 1990, we'll say that's about 1990, all the way to 2010. It shot up pretty fast because at 1990, it went from 3.85 to 4.13 to 4.83 to 5.78 to 6.77. So it was pretty much going up by millions each year. It was a greater increase. So now we're going to create a bar graph, population through the years. So population in millions. So this is what I did to show you. So I did our population in millions from 2.11 to 6.77 here. It shows that in 1960, our population was 2.11 million, and then 1965, it was 2.32. I mean, it just shows you how much it increased. And then you can see how everything slowly like raised up here. And then when you got here, it like shot up very quick. It wasn't just a gradual increase anymore. It went very fast. It was like a greater slant. Now, by looking at these, what is the maximum and minimum? Ooh. Okay, so the maximum we can either tell by looking at our I like using the bar graph because it shows more. So our greatest number was 6.77 million, and that was actually in 2010. So our maximum population is 6.77 million, and then our minimum, which is our smallest amount that we had, was 2.11 million, which was during the year of 1960. So that's pretty much how you find your max and your min. Your max is as high as your information goes, and then your minimum is as low as your information goes. Well, all right. I am done with my team teach. I hope you all enjoyed it, and I hope you all learned something. Thank you.